What if I told you that Formula One teams spend over £100 million a year engineering just two cars? 0.1% of the world's best engineers working obsessively to find mere hundredths of a second on track. This results in pistons that survive 20,000 RPM, brakes that reach over 1000 degrees Celsius, and gearboxes that shift in 2 milliseconds. From 50,000 pound pistons to 250,000 pound gearboxes, from carbon brakes that takes 3 months to manufacture to front wings that require a full week of continuous production. Today we are going inside the world's most advanced racing machinery to discover how engineers build something that operates at the absolute limit of physics. And trust me, the numbers will blow your mind. But before we dive into this engineering masterclass, make sure you hit that subscribe button. Our aim is to reach 50 subscribers by the end of this month. And don't forget to like this video. Before further delay, let's dive into our video. Let's start with something that might shock you. A single F1 piston, including development and manufacturing, can cost over 50,000 pounds. That's more than most people's cars for just one small component. But here's why. These pistons must survive 20,000 RPM. To put that into perspective, that's 333 complete cycles every second. At those speeds, the forces are absolutely brutal. At Cosworth, who've been making F1 engines since 1963, the process begins months before a single piece of metal is even touched. Engineers start with fundamental questions: V10, V8 or V6, bore and stroke dimensions, valve positioning. Every decision affects the piston's design and there is no room for error. The part that gets the most attention is the crown, the top surface facing the combustion chamber. Using advanced software, engineers create detailed models, analyzing inlet and exhaust ports to optimize fuel mixture and combustion. Computer simulations reveal stress points and heat loads. Engineers continuously refine the crown shape to reduce stress while maintaining combustion efficiency. They are walking a tightrope between performance and reliability. The tolerances are absolutely mind-blowing. Piston rings and their grooves have tolerances of just 10 to 20 microns. That's 0.01 of a millimeter. To put that into perspective, a human hair is about 70 microns thick. Each piston starts as a simple aluminium billet, heated to between 400 and 500 degrees Celsius, then shaped through forging. The forge tool itself is a masterpiece, made from tool steel and super finished to be perfectly smooth. After forging at those high temperatures, the aluminium must return to T6 conditions, essentially the strongest possible state for this type of aluminum. This involves heating in an oven, then rapid cooling with water, air or oil. The precision reaches almost unbelievable levels. Each piston requires 30 to 50 different machining processes, taking between 2 to 6 hours on machines that cost hundreds of thousands of pounds. Here's something incredible. If you just held the piston for about 10 seconds, it would go out of tolerance. That's why machining takes place in temperature controlled rooms. And here's a secret most people don't know. The pistons aren't actually round. They're deliberately made oval. When engine runs and stresses deform the piston, it becomes optimally round. It's engineering genius. Moving from piston to gearboxes, and these are even more expensive. F1 gearboxes cost upwards of 250,000 pounds each, and a team's total gearbox spend reaches around 5 to 6 million pounds per year. At Alpine, you can find a development gearbox with a transparent casing. This isn't what they use on the car. It's for designers to see exactly how oil flows around the inside. Unlike your road car, an F1 gearbox is what engineers call a stressed member. The engine bolts onto the monocoque, the gearbox bolts directly onto the engine, and the rear suspension bolts onto the gearbox. Remove the gearbox and the car would literally fall in half. Despite this structural role, the casing is surprisingly thin. At TDF, you can find a real gearbox made from 3D printed titanium with carbon patches in strategic places. Engineers machine away titanium and glue in carbon fiber just to save a few grams. And here's something interesting. The gears aren't arranged in order. You don't have 1st through 8th laid out sequentially. Lower gears sit closer to the bearings because they face a higher torque and need better support. Modern F1 cars have what it's called seamless shift, essentially zero time between gear changes. To achieve this, cars have two selector barrels. One engages the current gears while the other prepares the next. This speeds up gear changes to as low as 2 to 4 milliseconds. The entire gearbox relies on just one oil pump that circulates around 1 liter of oil. The oil journey is straightforward, pumped into the gearbox, sits as a reservoir at the bottom, goes up to the spray bar, sprays into all the gear ratios and differentials, then falls back down. The differential handles 1000 horsepower and must manage massive forces. It has a built-in clutch that adjusts the amount of slip between wheels. By the time the car is in a straight line, both wheels rotate at exactly the same speed. Between practice, qualifying and races, each F1 car covers about 30,000 kilometers per season. That means each gearbox must survive around 5,000 kilometers. Not much for a road car, but incredible considering the abuse they endure. The entire F1 braking system costs around £100,000, and there's a good reason for it. These brakes stop an F1 car from 200 miles per hour to 60 miles per hour in just 3 seconds. That's a deacceleration so extreme it hits nearly 6 Gs. Enough force to make it almost impossible for a normal person to keep their head up. And these brakes reach temperatures of over 1000 degrees Celsius, about as hot as lava. While regular materials would melt, carbon fiber F1 discs just keep performing. In terms of lap time, consider this: 2 cars flying down a straight at 200 miles per hour. The first brakes 100 meters before the corner, the second at just 90 meters. That 10-meter difference translates to 0.078 of a second faster, almost a tenth. Over an entire lap, better braking makes the difference between winning and losing. When the driver presses the brake pedal, brake fluids get pressurized through hard brake lines. For the front, fluid flows through steel braided tubing inside the wishbone to reach 6 pistons inside each caliper. At the rear, brake-by-wire technology comes into play. The system measures regenerative braking from the electric motor. If the car is storing energy, less brake pressure goes to the rear wheels because the car is already slowing. Even the brake pedal is engineered to perfection. Made from a single piece of carbon fiber, it's designed for each driver's feet. Team actually scan driver's feet and cut the pad to suit each driver. The pedal sees about 180 kilograms of force, 3 times the driver's weight. At Brembo in Italy, they supply every F1 team with calipers and half the grid with brake discs. Each caliper is machined from a single aluminium alloy block using topological optimization, software that puts material where it's needed for stiffness and remove where it's not. The brake discs start looking like thick felt, actually carbon strands with no glue or resin. Through a process called needling, they press the fiber mechanically to get the basic shape. The disc then goes through carbonization, heated in an oven. Then a second heating process with methane gas. Carbon and hydrogen from the methane are separated, with carbon filling the pores in the structure. This process takes an astonishing 2 to 3 months. Once ready, precision machining begins. The most time-consuming part is drilling up to 1200 cooling holes, each exactly 3 millimeters in diameter, the minimum allowed by regulation. The machining process takes around 15 hours per disc. Despite all the forces involved, modern F1 carbon discs have incredibly low wear rates, 0.01 millimeter per kilometer. In a race weekend, you might wear your pad by just 1 millimeter. Something like a front wing takes 7 full days of around-the-clock work to manufacture. But the front wing isn't just about creating downforce. It controls how air flows over every other part of the car. At Alpine F1, the design process starts with pages of technical rules from the FIA. These aren't just measurements, they describe exact shapes, specific curves, and set boundaries for where parts must sit. The design process starts in CAD, then moves to CFD, Computational Fluid Dynamics. Teams are limited to about 2000 CFD runs every couple of months. Each run tests specific wing shape. Once CFD shows promise, designs move to wind tunnel. While CFD uses simulated air, the wind tunnel uses real air flowing over a real model. But wind tunnel time is precious and restricted by regulations. Jacob, a composite design engineer at Alpine, turns aerodynamic shapes into parts that can handle brutal F1 forces. Using finite element analysis, they examine everything from material thickness to how different carbon pieces bond together. Production starts with a pattern cut from high density foam to make a carbon fiber mold. They use carbon for the mold because it has the same thermal expansion as carbon fiber parts, ensuring more accurate components. Producing the wing is a massive job. 7 days, 4 or 5 people each shift. Day shift, night shift, weekends. Each carbon piece is cut to shape on a giant computer-controlled cutter. The team uses laser system to line everything up perfectly. It projects target points around the mold, finds where the mold is in the room, then projects the correct ply. This saves enormous amount of time and ensures precision. Once all layers are in place, anywhere from 3 to 100 depending on the part, it goes into a vacuum bag, then into the autoclave. There's pressure from inside and outside, pushing all materials into corners while heat makes the resin flow and cure. Before seeing a racetrack, each wing goes through a rigorous crash testing with Cranfield University, with the FIA watching. Each wing must slow the car down gradually without exceeding 40 Gs of force to protect the driver. F1 suspension isn't just about handling bumps. It's fundamentally about the aerodynamics and maintaining the perfect gap between the car's flow and the track for maximum downforce. In the 90s, team developed active suspension, computer-controlled systems that kept the car's flow the perfect distance from the ground. It worked brilliantly, but quickly banned. Williams actually tried removing springs and dampers entirely in the 1980s. While the aerodynamics were better in theory, drivers couldn't handle the vibrations. F1 cars use double wishbone suspension with carbon fiber wishbones. What you see on the car isn't the structural part. There is a structure inside the shroud, giving opportunities to change shapes aerodynamically. Hidden inside are 3 Xylon tethers, special Kevlar straps that keep wheels attached during crashes. There is also wiring connecting sensors measuring wheel speed, temperature, and load cells. The front uses a push rod system while the rear often uses a pull rod. There is no performance difference. It's about packaging and keeping the top of the gearbox clean for airflow. Instead of traditional coil springs, F1 uses torsion bars. Much neater from packaging perspective. Teams can change stiffness by adjusting thickness, length, and leverage. The heave spring is F1's clever solution to managing massive aerodynamic loads while staying supple in the corners. It uses small donut-shaped wire meshes that act as a hard spring, preventing the car from dropping too low under maximum downforce. The anti-roll bar is another torsion bar running down the center of the main torsion bar. Same function as road cars but packaged much neater, taking up significantly less space. What I love about Formula 1 is the constant push to the absolute limit of what's possible. Every component pushes boundaries, every gram matters, every micron counts, every millisecond is fought for with obsession. This is what happens when thousands of the world's brightest engineering minds focus on a single goal, going faster than anyone thought possible. That's it for today's video, guys. If you're liking the content, do not forget to subscribe to our channel. Our aim is to reach 50 subscribers before the end of this month. And if you love the content, smash that like button. I'll see you in the next video. Until then, take care and goodbye.